Our brain, our biological brain, is a couple of recurrent neural networks. So you can consider it as a recurrent neural network of recurrent neural network. And that's why the study of nonlinear dynamical systems, how it works, is very important. Neural ODE is just one of the paradigms that people are recently doing. And instead of, for example, backpropagation, they use this technique in order to get around calculating the complexity of calculating the gradient of loss. And in this playlist, I want to talk about nonlinear dynamical systems, but one of the simplest approaches that I've seen in the literature is that they linearize this nonlinear system, and around that locally, around that fixed points, you see that it works as a linear system. The nonlinearity can be approximated by a linear system. And so everything that you know from linear systems can be applied. But around a neighborhood of another fixed point, everything is different. And there are always some noise that they may drive to another fixed points. And sometimes they create chaotic phenomena. But locally, you can do everything you want. Locally, you can do lots of things. You can say that I can approximate it by a linear system. But globally, you cannot do that. You cannot connect those things. So it becomes very complex, because a simple noise can drive you to a different fixed point, or even a limit cycle. So it may converge to this limit cycle, and from one initial points. So in this lecture, let's focus on this article, this beautiful article, which is about a different paradigm on how we learn and how we calculate the gradient of loss. But I've also explained this one in a different lecture. Also this one in another lecture. But I haven't explained this one, which is also important. But it's very easy. So the idea of this NIPS article is that what happens when we add more layers and we take smaller steps. This is a recurrent neural networks. F could be anything. For example, for GRU, for LSTM, for different models for recurrent neural network, we have a different F. But if you add the number of layers, because each one you can extend the number of layers. And also, because we have a recurrent neural networks, for example, in a language model, from one time step, the other time step, you have different inputs at another time step, but the hidden states are used. Because you are using different time steps, what if the number of time steps becomes you have lots of time steps, and you're also adding some layers on top of that, and at the extreme configuration, you will see that it's just this ordinary differential equation. So when we add more layers and take smaller steps, this is what you want. This is what happens. And you see that you can apply it for residual network, like the left one, and the right one, which is in the ODE, that transforms the state. And the motivation is that we show how to compute the gradients of a scalar valued loss with respect to all inputs of any ODE solver without backpropagating through the operation of the solver. And not storing any intermediate quantities of the forward pass allows us to train our models with constant memory cost as a function of depth, a major bottleneck of training deep models. So you know that Z is just this one. For example, just the solution of this differential equation. And if you write it, so Z of T1 is this. Z of T1 is this. So if you want to calculate the loss at any given point, it's like this term, loss of this term. But this term can be just, you can solve it with just MATLAB, Python, or any library that you like very easily. But the idea is very classic, very, very classic. And this approach computes gradients by solving second augmented ODE. So we have a differential equation, and we also have an augmented A. A is augmented differential. If we couple them together, so this becomes an augmented system. If you solve this, then you can deal with this loss and also with this gradient much more easily, and you will see how it works. So to optimize L, we require gradients with respect to theta. So the first step is to determine how the gradient of the loss depends on the hidden state Z at each instant. So Z is our hidden state. So we define this adjoint, which is the gradient of loss with respect to your hidden state. And it's just, if you work on that, you will see that if you differentiate with respect to t, then it becomes this equation. And now computing the gradients with respect to loss can be written in this form. This is what we need, because first of all, the vector Jacobian products can be efficiently evaluated by automatic differentiation. And now that you have this augmented dynamics, I mean, not only your hidden variables, but also your augmented variables. So for any initial condition, you just run this dynamics on an augmented state, and you compute this vector Jacobian products. So we compute this, and then you solve it in reverse time ODE. So instead of going from T0 to T1, you go in the reverse direction. So you get T0 and Z of T0. And that is what we want, because if you calculate the gradient with respect to theta, as well as your gradient of loss with respect to your hidden variable, then you can do all of the updates, and you can do it more efficiently than backpropagation. And you can use it for time series model or even normal flows or even ResNet or any recurrent neural networks and any application. And so you can use it for a generative latent function time series model, which is really interesting. But in the next lectures, I will focus on different aspects of recurrent neural networks, because I think the best way to model your brain is to consider as a coupling of a couple of recurrent neural networks. If we understand the dynamics of that, then we can understand the brain more efficiently. And people in Google Brain, Google AI, have written an article which is called RNNs of RNNs, which I will explain it. And they extended the contraction theory, which is a very elementary things in classical nonlinear control, as well as classical nonlinear dynamics and those things. that they define Lyapunov functions, but instead of defining that, we have a better approach, that we have the idea of contraction, that if we have two initial states, for example, this one has this trajectory, but this one has another trajectory, but after a while, their trajectories, the difference between them, so this difference is large now, but it becomes smaller until it converges. This is the idea of that contraction theory. So the idea of this article that I will explain is that they extend it for coupling of recurrent neural networks. Each recurrent neural network has a feedback to itself, and so it becomes a very interesting mathematical object. And you can apply it for many problems in mathematical biology, mathematical neuroscience, as well as deep learning, to have more efficient, much more efficient methods than just your traditional deep learning, which has lots of problems. So the more we draw inspiration from our brain, which is just a miracle. Who designed that? I don't know. Who designed DNA? I mean, the probability that somebody designs a watch or an iPhone or something like brain is zero because of the complexity of that, because it's very unlikely to be created just by evolution. But if we understand these recurrent neural networks, we can understand, for example, we can connect different parts of the brain. For example, how hippocampus is working with amygdala. Amygdala is responsible for your emotions. How it is how it is coupled with prefrontal cortex, which is the basis of your reasoning in your brain. How these couplings are working. So it's very interesting. So you're connecting your reasoning. So the way the brain uses reasoning is totally different from the way our algorithm. For example, I have a playlist for reasoning, but if you combine all of those ideas, you will see that our brain has a different paradigm. That's why it's more efficient. First of all, our brain is distributed. Second of all, it is asynchronous. And also it is spiking, and also it creates bursts in your neurons. Also it has some other structures such as astrocytes, networks. And so it's very interesting. So this playlist that I'm talking about, this RNN dynamics, is very rich. It has a very rich literature, but very few people are still aware of that. Very few people are still aware of the importance of these ideas, of using the ideas of dynamical systems for natural language processing or for any machine learning task. And we can even rewrite all of the machine learning using dynamical systems. And dynamical systems is much closer to our biological brain. Mathematics of dynamical systems is much more important and in comparison to our naive backpropagation algorithm that we are just creating problem for ourselves rather than developing a theory. So this is what you will see in future, especially in the next 9 years. For example, in 2032, you will see more about these dynamical systems and how you can use them to train your recurrent neural networks. Because training a recurrent neural network still is expensive. And people, for example, when people use transformer architecture, they do not understand that you are adding lots of complexity. And by defining, for example, keys, values, and queries, the three matrices, you're defining lots of complexities. But what the brain does is different from this. The brain, for example, associative memory is a very important part of your brain. When you think of a word you associate it with another word. For example, when I hear recurrent neural networks, I associate it with dynamical system. And then suddenly my mind associates it with our brain. Then I remember neuroscience. So this happens lots of time, and sometimes it has very chaotic trajectories, and it happens in just 1 minute. And that's why you can talk about a very abstract thing, very complex thing. So it's just like a miracle that we can do these things, and it has become very ordinary that our mind can think about these things, and we think our brain is ordinary, but it's just a miracle. Even a simple reasoning is very beautiful, very interesting.